Welcome to lecture 12 of Machine Learning from Data, Regularization. Now this is a tool to combat overfitting, so it's important. And what's overfitting? We discussed this last time. It's fitting the data more than is warranted. And here's a classic example of overfitting. You have this blue target function, a few data points generated with some noise, and you throw at it a reasonably complex hypothesis set, and you fit, and you get this red curve, which is nonsense. Okay? So we drilled down. What causes that red curve, which is nonsense? Okay? And we identified noise as the primary cause of this overfitting. Okay? And what is noise? Noise is the part of the y value you cannot model. But this y value is present in the data, so even though you cannot model it, you try to model it and are led astray, and this hurts the learning. Okay. Now there are two kinds of noise. The first is what we are very familiar with, these random measurement errors as illustrated by this garbled picture of the elephant, and we call this stochastic noise. It's no surprise that if you have these random measurement errors, it's going to lead learning astray. The interesting case is deterministic noise. Okay. Now deterministic noise is coming from an overly complex target function. A target function which is more complex than the capabilities of the learner, the hypothesis set. Okay, so this means that the target function has nuances and complexities that cannot be modeled. These nuances are present in the data. The learner tries to model those nuances and gets led astray, and that hurts the learning. So stochastic and deterministic noise, you try to model them, but you can't model them, and that hurts the learning. Now, this deterministic noise is illustrated, nicely by this picture of the elephant, which appears in the, 3-year-old's picture book, where, we try to remove the nuances and complexities in presenting the data to the 3-year-old, because it's easier to learn when the nuances and complexities that you cannot model have been removed. So we're trying to remove this deterministic noise in order to help the 3-year-old. Humans, tend to be very good at, extracting the simple pattern, finding the basic idea, ignoring the noise and the complications. But imagine showing this, this picture of this garbled elephant to a computer. It's going to pay equal amount of attention to all the pixels. So it needs help to simplify. It can't do it automatically. Now, one way to help is to extract good features, summarizing the essential relevant information. And that happens before learning. Now, once you have got your good features, setting a good baseline for E in and E out, as you're learning, now at some point you start fitting the noise, you start overfitting, and that's where regularization can help. During the learning, when you start fitting the noise, you can apply the brakes. Okay, so that essentially, in a nutshell, is regularization. Regularization is this cure that, this cure that prevents the tendency to fit the noise, to get distracted and be led astray. Okay, so, and by preventing you from fitting the noise, you improve the out-of-sample error. Okay, so how does it work? Basically, the idea is, in order to prevent you from fitting the noise, we have to constrain you somehow. Okay? And that way, you cannot fit the noise. But if we constrain you somehow, maybe you cannot fit the target function. Okay? So that would be a side effect of this cure, regularization. And we must make sure that the side effect doesn't, overpower the actual benefits. Okay? The benefit being you don't fit the noise. The side effect is you might not fit the target function. You might not fit the signal. Now, regularization, we are to some extent familiar with it, although we may not have looked at it as regularization. So think, the young child who's got this complex neural network trying to represent reality, and all around you is all this complexity and randomness, and you can go this way and that way, and you'll get totally led astray by all the complexity that's out there. And then your parents and mentors and all the people who influence you come along, and they constrain you, they focus you on basic principles and bring you up. So in some sense, we're all regularized by our parents. Otherwise, we would go on and overfit all the complexity and all the randomness that's out there. Okay? So it's a good thing that, the parents came along during our learning, regularized us so that, we have a better out-of-sample outcome. So we're all regularized by our parents. Now, when it comes to the machine, okay, we need to make sure that, the regularization, while constraining the model, doesn't have too much of a side effect. So let me show you in a very simplified setting, the potential benefits of constraining the learner. Okay, and here's an example that we saw before, okay, when we talked about bias and variance. So, you have a target function in blue, and we generate data sets, and, you produce this wild assortment of linear fits, okay, completely wild. Okay. And what would it mean to constrain the learner? So, for example, we might say, you're not allowed to fit with huge slope. Even if the data warrants a huge slope, you must do the best you can with small slopes. So let's say we constrain the weights. The slope is one of the weights. So let's say we constrain the weights to be smaller. Look at what happens. It significantly reduces the wildness in the fits. Okay. Now, the question is, does it work? So let's see who the winner is. Okay. So on the left, if we repeat many times, on average you get this red fit. And the wildness, the variance in the fit is captured by this gray region. Okay. And on the right, the constrained, the smaller weights fit. We'll call this the regularized fit curve. I'm constraining the learner. You get almost the same red curve on average. So on average, you're almost fitting the same, but look at the variance, the gray region. The wildness is significantly reduced. Okay. And, so when you look at the numbers, and we saw this before, the bias is 0.21 for the case of lines with slope. And when you constrain, okay, it hurts you a little bit. The bias goes up to 0.23. So that's the side effect of this constraint, this regularization. Here's where we gain big time, okay? And it's the gray region. The variance drops from 1.69 to 0.33. The variance drop is huge, more than warranting the side effect. So we have sort of significantly decreased the variance at the price. The cost is a small price that we pay in the bias, the side effect. And we had this decomposition of the out of sample error. It's the sum of the bias and the variance, and so the bias and the variance with the regularized fit is much better. Okay. So the constrained regularized fit is much better in this example. And now I'm going to remind you, we also studied the constant model, okay, when we compared this line with slope with just the flat lines. And the constant model had a bias of 0.5 and a variance of 0.25. So the sum is 0.75. So the regularized fit even beats the constant model. So it turns out to be better to have the extra flexibility of the lines with slope as opposed to just the flat lines. So it turns out better to have this extra flexibility of the lines with slope. It turns out to be better off to have a complex neural network in your brain. Okay? But if you just let it go wild, you're in this world of no regularization, and then it ends up being much worse. Okay? But if you have this extra flexibility, but you have a way to systematically, rein in the fitting power, to systematically apply the brakes, to systematically regularize, then you can beat the simpler model. Okay? So the complex model with the ability to brake is better than the simple model with full capability. But the complex model without the ability to brake is a disaster. And that's that red fit, that total disaster that we saw at the beginning. So, okay. So, now we're going to discuss the mathematics. It's going to get a little bit dense. We have to, we have to figure out how to mathematically implement regularization in some of our favorite machine learning models. And so, we'll derive regularization, from starting from some concept similar to the VC theory. Okay, and at the end, we're going to derive this very popular method of regularizing called weight decay, and then we'll see some experiments and some results. Okay. So let's move to the board. Okay, fasten your mathematical seatbelts. We've got some intense derivations ahead of us, but, don't panic. I'll give you a quick overview. So starting with, we'll start with a high-level view of what we're trying to accomplish, okay? And then we'll focus in on the concrete linear model, specifically linear regression. That's going to be mathematically the easiest to sort of expose the ideas, okay? And then actually get a working algorithm. And one goal is to show you how, this example that we saw where we constrained the fit to have small slope, lower weights, show how that helps. Okay, so link constraining the model to better generalization. Okay, and that's going to lead us to the hard order constraint and then the much more mathematically convenient soft order constraint. Okay, and so then within this soft order constraint world, we're going to do the mathematics for the linear model and actually develop the algorithm. And it's going to be very similar to the pseudo-inverse algorithm. So we will have a very concrete model, the linear model, okay, the regression model, which is actually quite powerful because we have, nonlinear transforms which can take us to arbitrarily complex spaces. Okay, so we have this concrete model, and then we will have the concrete mathematics and the algorithm developed within that setting, and it's nice and clean, and we can see exactly what's going on. And we will develop, this very popular form of regularization called weight decay. And then, that doesn't, now we're not going to be prevented from using this weight decay technology whenever we do machine learning and similar constraints, okay, with this sort of, clean mathematical derivation as sort of the reasoning for why we use regularization. Okay, so let's begin. Okay, so at a high level, what are we planning to do? So I'm going to remind you of the VC inequality. So E out of G is at most E in of G plus omega, so an error bar. But what did this error bar depend on? It depended on the hypothesis set. Okay, so on what's it saying? What it's saying is that if you can get a comparable error in sample, using a simpler hypothesis set, then you expect the out-of-sample error to be better. So fitting with simple H is better. Okay, and now, what our plan is to sort of take this a step further. So that's what regularization does. It takes this a step further and says, well, if it's better to fit with a simpler hypothesis set, then maybe it's also better to fit with a simpler hypothesis. So we're going to try to replace this with, some error measure, some error bound, some error bar, let's say, heuristically, that says that if you can get the same in-sample error with a simpler hypothesis, then you are expecting a better out-of-sample error. Okay, so we're going to try to replace this with something like an omega, an error bar that depends on G, and sort of quantifies the complexity of the hypothesis. So replace the error bar, which depends on the hypothesis set, with an error bar, not quite a rigorous error bar, but some quantity that behaves like an error bar that depends on the hypothesis, measuring its complexity, penalizing you for a more complex hypothesis. Okay. And there are several questions, does it work? And, so first of all, does it work? And second of all, how do you measure the complexity? And third of all, how do you even implement such things? Okay. So that's, part of what we're going to describe today. Okay. Now, to make things concrete and mathematically manageable, and so that we can have clean derivations to expose the theory, we're going to work with linear regression. Regression turns out to be simpler to work with, and linear models, are easy to mathematically manipulate. So let's have a quick review of linear regression, because that's the context in which we're going to make most of our discussion. Okay. So remember, in linear, in general, you have your original X space. So you have your data X1, Y1, X2, Y2, and so on up to Xn, Yn. Okay. And, we're going to allow now for the nonlinear feature transform. So even though we are narrowing down to this concrete case of linear regression, you get immense power by being able to go to an arbitrarily complex, feature space using any feature transform you want. So, if you transform this data, remember you only transform the X values, and so this becomes a Z1, Y1. You don't transform the Y values, Z2, Y2, up to Zn, Yn. Okay, so this is the transform data. Now, when we went into the linear algebraic world, we represented this data using a data matrix X and a target vector Y. Okay? And similarly, you have a transformed data matrix Z and a target vector Y. So the target vector doesn't change. Now, how does the linear regression work? It find the weights W tilde, Y W tilde, because these weights only exist in the transformed world, but, miraculously, that they allow us to perform a nonlinear, to fit with a nonlinear function in the original space. And when we want to predict, we take a point, transform it, and then apply this guy. Okay, so find weights that basically fit the data. Okay, that minimize the squared error, which is ZW tilde minus Y transpose ZW tilde minus Y. So these are the deviations between the predictions on the data and the target vector on the data, and this is the norm of the difference between the prediction vector and the target vector squared. So the norm squared, so we're minimizing the squared error. Okay, there's a 1 over n, but that doesn't affect the minimization. Okay, and when you perform this minimization, essentially what you're doing is you're trying to get your predictions ZW tilde to be approximately equal to Y. And if Z was invertible, we could just multiply both sides by the inverse of Z, and we would have W tilde is equal to, the inverse of Z times Y. But if Z is not invertible, and that's generally the case because you have more data points than dimensions, okay, it's not even a square matrix. So instead of the inverse, you use the pseudo-inverse. And we call this the pseudo-inverse algorithm. And when Z transpose Z is invertible, Z pseudo-inverse is equal to Z transpose Z inverse, Z transpose. Okay, when this guy exists. Okay, so that's a quick review of linear regression. Okay, and basically it says that, we can efficiently solve the linear regression problem, the fitting problem, in any feature space by pseudo-inverting the transformed data matrix. Okay, so it's a very nice, clean algorithm. Okay, now, This is a feature transform phi. And we're going to be working with the polynomial feature transforms, and I'm going to take this opportunity to introduce you to a particularly nice, convenient, mathematically well-behaved version of the polynomial transform using the Legendre polynomials. So don't panic, it's just the Legendre polynomials. So, we take our vector 1x in, let's say, one dimension, and we transform it to L1 of x, L2 of x, LQ of x. Okay? And so this is the first Legendre polynomial, the second, the third, and so on, the qth Legendre polynomial. So this is exactly analogous to the qth order polynomial transform. In fact, this is a first order polynomial, this is a second, third, fourth, and so on, qth order. So it's exactly analogous. It's more convenient to manipulate these guys than the standard polynomials, and also, they satisfy mathematically interesting properties, mathematically very useful properties, and also visually they give the right visual of increasing in complexity as you increase the order of the polynomial. So for example, if you looked at x cubed versus x to the 5, they are both functions that increase like that and they look equally complex. Not so with the Legendre polynomial. So let me show you what the Legendre polynomials look like. And you can see all the details in the text. Okay. So the first order Legendre polynomial, L1 of x, is just linear, just like x, okay? And it's a polynomial of degree 1. L2 of x is quadratic. Well, it's quadratic with a shift and a scale, okay? Then L3 of x, okay, this is now a cubic polynomial, and it goes, it has one wiggle, okay? Nice. L4 of x, okay, has two wiggles. Okay, L5 of x, okay. Wow. And L6 of x, we can even go to L6. It looks like this. Wow. Okay. So what do you observe? What you observe is that as you increase the order of the polynomial, they're clearly getting more complex, intuitively, more wiggles. Okay, so that's nice because we're going to start talking about complexity and constraints and so on and so forth. And now you get the image that if I restrict you to using only the first two Legendre polynomials, so for example, the first two, or let's say the first three, it's considerably less complex than, let's say, allowing you to use sixth order polynomial. Because look at the number of wiggles you can introduce by taking linear combinations that involve that guy. Okay. Although technically speaking, all polynomial transforms can give you the same set of functions that you can ultimately implement with linear combinations. Here we see naturally the increase in complexity. There's another very nice property of the Legendre polynomials, which is that they are orthogonal. They're an orthogonal basis for polynomials, where the inner product is with respect to the uniform measure on -1 to 1. Orthogonal basically means independent, some sort of more formal notion of independence, in the sense that if I tell you to dial down how much of L6 you have, it's not affecting how much of L3 you have. They're sort of independent. And so by telling you to dial down the coefficient of your sixth order Legendre, I'm effectively telling you to dial down this mode in your function, which means I'm telling you to dial down this highly complex mode. If I tell you to dial these guys down, I'm telling you to dial down complex modes and keep only simple modes. So I have a way to control the complexity of a function by deciding how much weight I allow you to put on each of the various more increasing complexity Legendre polynomials. Okay, so very mathematically convenient. Okay, and at the end of the day, they're equivalent to polynomial transforms anyway, so, there's nothing wrong with choosing this more mathematically convenient set of polynomial transforms. And with that said, we'll go back to the general notation using phi. Okay, but bear in mind that, for all of our discussion, we are mostly focusing, we have as a concrete example the Legendre polynomials. Okay, so it's polynomial transforms, for which we can get this nice orthogonal basis that increases in complexity. And with that said, let me introduce you to two hypothesis sets. H2, okay, the second order polynomial fit. So it's h of x, corresponding to the second order Legendre polynomial transform with q equals 2. So h of x, where h of x is equal to w0 plus w1 L1 of x plus w2 L2 of x. And w is in r cubed. So you have three parameters. And h10 of x, hypothesis set 10, which is the hypotheses, the functions where h of x is equal to w0 plus w1, L1 of x, plus up to plus w10, L10 of x. Okay, where w is in R to the 11. So these are just two concrete models. If I wanted to generalize, I could define HQ, where the functions are of the form sum from I equals, or from little q equals 0 to big Q of WQ, LQ of x, where L0 of x, it turns out the zeroth order Legendre polynomial is 1. And all these Legendre polynomials are pairwise orthogonal with respect to that uniform measure. Okay, now, here we have the second order polynomial fit. Here we have the 10th order polynomial fit, formally represented as hypothesis sets, okay, with different feature transforms. Now, what should be clear is that the second order polynomial fit, H2, is a subset of H10. What does this mean? What this means is that H2 is a simpler hypothesis set. So, if E in of H2 is approximately E in of H10, so what does that mean? That means that if you had chosen the second order polynomial fit, you get some in-sample error. You fit with the 10th order polynomial, you get pretty much the same in-sample error. Okay. So if the two in-sample errors are comparable, you would be better off having chosen H2, because H2 is simpler. So you expect, H2 fit will be better because it has a tighter link to E out. Again, that's coming from the sort of the VC theory. So if you manage to fit equally well with a simpler hypothesis set, then you're better off. Okay, it's better off to fit with a simpler hypothesis set. Okay, so now what I want to do is show you that effectively what that means is that if you can constrain the model and fit equally well, then you're better off. So I'm going to translate this into the language of constraints. Okay? And I'm going to show you that H2 is just a constrained version of H10. Okay? And then that tells us that if you can fit while constraining yourself, you're better off. Okay? Because we already agreed that if you can fit with H2 just as well, then you're better off with H2 than H10. And I'm going to show you that H2 is a constrained version of H10. So that means if you can fit under constraints just as well, then you're better off. Okay? And here, look, H2 is equal to the hypotheses H of x, which are of the form H of x equals W0 plus W1 L1 of x plus W2 L2 of x plus W10 L10 of x, okay, where W is in R to the 11. And you say, well, wait, that's just the 10th order polynomials, except I haven't put the constraint in yet. So let me put the constraint in. Okay, what's my constraint going to be? And it's, not going to be a surprise. I'm going to require that W3 equals W4 equals W5 equals equals W10 equals 0. Wow. What a pedantic way to write the second order polynomial fit. Yes, the second order polynomial fit is the same as doing the 10th order polynomial fit, but constraining yourself to having all the weights bigger than, so W3 to W10 having all those weights equal to 0. Yes, that's indeed true. Okay, but I'm just trying to make a point here that, the simple hypothesis set is just a constrained version of the more complex hypothesis set. Okay, and now I'll repeat that argument. If we can fit equally well with the constrained hypothesis set, we are better off. Okay. Now, this we call the hard order constraint. Hard order constraint. Okay, good. Now, turns out that the hard order constraint is hard to work with. Okay. Now, why do we call it the hard order constraint? Not because it's hard to work with, but because it sort of explicitly sets some of the weights to 0. It's kind of like, it sets it in a hard way. It's kind of like the hard threshold. It's just 0. You cannot deviate from 0. Okay. It's tough to work with mathematically. It's hard to work with mathematically. So, continuing with this philosophy that if I can fit with a constrained hypothesis set, I'm better off. Okay? Let's introduce the soft order constraint. Essentially, let's soften this requirement that the weights, the higher order weights, should be 0. Okay? And I'm going to define h sub c, okay, which is equal to the 10th order polynomials, h of x. So the 10th order polynomial fit, where h of x is equal to w0 plus w1, L1 of x plus w10, L10 of x, okay, where w is in R to the 11. Okay. And now, instead of explicitly setting some of the weights to 0, that's the hard order constraint, I'm going to give you a budget C. Okay. And I'm asking you to fit while being constrained to not, to not go over your budget. And what does that mean? That means that the sum of your weights, okay, should not go over the budget C. Well, actually, technically, I'm going to require that the sum of your weights squared don't go above your budget. So that any time you decide to add weight to one of the modes, anytime you try to add weight to one of the orders, you're going to pay a price. Okay. And so we want the sum of, from I or from Q equals 0 to 10 of WQ squared to be less equal to C. So I'm giving you a budget. So we call this a soft order constraint because it's not explicitly setting some of the weights to 0. It's giving you a budget. It's encouraging the weights to be close to 0. And it's encouraging all the weights uniformly, saying, I don't care how you fit, but just stay within my budget, please. Okay? And this is a constraint. It's also the case that H sub C is a subset of H sub 10. But now so the same argument applies. Okay, so this is a constrained version of H sub 10. It's a simpler version of H sub 10. So if I can get a comparable fit with H sub C, then I'm better off. Okay, if I can fit equally well with a simpler model, with a constrained model, I'm better off. So now we've linked, constraints to being better off out of sample. And so that shows how if we can, while we're performing the fit, if we can implement a constraint and do just as well, then we're better off. Okay. Now, let me point out that, the soft order constraint is nice in another way, which is that, when you're talking about the hard order constraint, where you set some of the weights to 0, I can either choose H2 or H10. In the soft order constraint, I have a knob C, and I can choose the amount of the constraint, the strength of the constraint. Okay. If I make C go to infinity, then I'm basically recovering H10. So you can think of C as defining the degree of the constraint. So if I had H2 here, and H10, which is the super complex model, okay, then C allows me in some sense to explore this territory. Choosing C allows me to sort of explore models of, varying degrees of constraint. And if I send C larger and larger, I eventually recover H10. C equals to infinity, no constraint. Okay. If I start bringing C smaller and smaller, I'm getting simpler and simpler, coming closer towards H2. And eventually, if I set C almost 0, then I'm even getting simpler than H2 and getting just to the single hypothesis, which is all 0. Okay. So that's the one nice thing about this constraint C. Okay. It allows me it gives me a dynamic range that I can play with. Okay. All right. So, summary. We've linked we've linked fitting with a constraint to accomplishing better out of sample error because you get better generalization, providing you can get a comparable in sample error. Okay, so what's left? What's left is to then figure out, okay, so how do we go ahead and do that? How do we fit under a constraint? Because now we have sort of understood that it's a good thing to do. If we can get a good fit with under a constraint, then it's a good thing to do. Okay, so then the question becomes, how do we do it? So let's erase. Okay, and let me just mention that everything I said doesn't rely on the fact that these are Legendre polynomials. I could put in any feature transform here. So our discussion has been basically general, but we've, made it concrete with the Legendre polynomials. Okay. Okay, so having discussed the philosophy of why it's good to fit the data with a constraint model, let's now talk about the mathematics, the mechanics of doing so. Okay, so, now even though we're in the transformed linear space where the weight vector is W tilde, I'm going to not put the tilde anymore, to just save a little bit of confusion and notation. Okay, so our hypothesis is W transpose Z and we have the budget constraint W transpose W less equal to C. Okay. And we're trying to minimize the in-sample error subject to this budget constraint. So we have the in-sample error of W is 1 over n, Z W minus Y transpose Z W minus Y. Okay. And if we didn't have the budget constraint, let's say that the solution is W lin, so I'll call this the linear fit without the constraint, and this is equal to Z pseudo inverse Y, which is Z transpose Z inverse Z transpose Y when Z transpose Z inverse exists, if this exists. Okay, and that's great, and that's nice, that's the pseudo-inverse algorithm, but that's not what we want, because, we need to minimize the in-sample error subject to the constraint. So we have an inequality constrained minimization. So this is an inequality constrained minimization. Okay, and in general, those are hard problems, but in this case, this problem is manageable for a bunch of reasons. First is the linear model, so we can manipulate it. Second, this error function, the in-sample error function is a convex function, and so that has all kinds of nice properties. And so let's go and try our best to solve this inequality constraint minimization, and we'll make a lot of progress. Okay, let's sort of denote the solution. So the optimal constrained weights are W reg. So reg for regularized. So think of regularization now as synonymous with constrained. Okay, so I'm constraining your ability to fit by giving you a budget. Okay, so regularized means constrained. Okay, now let's examine the first case, which is easy. Okay, so the first case is that, your optimal linear fit, W lin transpose W lin. So your optimal linear fit satisfies your budget constraint. So this is case 1. So the optimal linear fit satisfies the budget constraint. Well, in this case, I can solve the constraint problem trivially. Okay? In this case, W reg is equal to W lin. Why? Because, you cannot get any weights that are better than W lin, and they satisfy the constraint. So the optimal weights satisfying the constraint cannot do better than W lin. Okay. So the first thing you do when you face such a problem would be to check if the unconstrained solution would work for you. If it would work for you, you're done. But, odds are it's not going to work for you. If you put any kind of a serious budget constraint in order to control overfitting, okay, then, that the whole idea is that this unconstrained fit is just wild, and it's the constrained fit that's, that's different from the unconstrained fit that's giving you benefit. Okay, so the second case is that the linear fit is not satisfying your budget constraint. Okay, so let me draw you a picture of what's going on. So let's imagine that this is the origin of your space, okay, and your budget constraint, basically, the weight constraint W transpose W less equal to C is basically, defining a sphere of radius square root of C. Okay, so I've defined a sphere of radius square root of C. Okay, so this is the square root of C. Okay, and this sphere of radius square root of C is called the feasible set, the feasible weights that satisfy your budget constraint. And this guy, the linear fit, is outside your feasible set, so it's somewhere here. Okay, now, what's nice about this error function, well, what we know for sure is that this error function, this in-sample error, is minimized here. And as you move away from this guy, the in-sample error is growing. And in fact, because this is convex, the way it's growing is very nice, that this is a unique, minimum and so on and so forth. Okay. In fact, this is much stronger than convex, it's quadratic. So if I were to look at what are called the contours of constant in-sample error, it's minimum here. And then, there's a region of the an elliptical region around this linear weights, okay, where you have a constant in-sample error, and then, if you move further away and further away and further away, okay, you get, the in-sample error is increasing as you move further away. So this is the minimum, then you get larger in-sample error, larger. And the idea here is that on this contour, of constant in-sample error. Okay. The in-sample error is constant along a contour, and as you move away, it's increasing. Okay. Now, just an important fact from calculus is that, okay, if I look at the gradient, so let's say I take a point on this contour, okay, and if I move the weights along the contour, there is no change in the error. So that means that the gradient of the error along the contour is 0. Okay, so if the component of the gradient along the contour, the surface of constant E in, the gradient along the surface of constant in-sample error is 0. So that means that the gradient of the in-sample error is always normal to the surface of constant E in. Okay, and that's a fact, that the gradient of a function defines the normal to the surface of constant value for that function. Okay. Now, let's see what's the basic idea. So I can choose any weights I want inside this feasible set. Okay, and here are the minimum weights. So the basic idea is that I might try to choose. The basic idea is that I should try to choose weights that are as close as possible to the linear fit, because then I'm moving towards moving down the contour hierarchy and getting onto contours that are lower and lower in sample error. So let us suppose that I pick this weight. Okay, could that be optimal? No, because look, if I move closer to the in sample to the linear fit, I move from this contour to a lower contour, thereby decreasing the error. So this cannot be the optimal. And in fact, you can easily convince yourself that no weights on the interior of this sphere can be the optimal fit to the in-sample error, okay, modulo this constraint. So what we conclude is that, the optimal solution that we're looking for has to lie on the surface of this sphere. So we will keep moving closer until we get to the surface and cannot move closer anymore. So here's a potential solution. Okay. Now look at this solution. And I'm going to draw another contour, a special contour, in the middle here. Okay. So, first observation. It suffices to find the minimum of this in-sample error subject to the equality constraint. Okay. So, the inequality constraint becomes an equality constraint. Okay. And so then we have an equality constraint optimization problem. Now, if you know all about Lagrange multipliers and so on and so forth, then you can go and solve this equality constraint optimization problem. Instead, I'm going to show you a geometric approach. Effectively, I'm deriving the method of Lagrange multiplier. Okay, but it's a nice geometric picture that gives you a little bit of an intuition for what's going on. Okay. So, let's look at this point, which has gone as far as it can while maintaining while staying within my set. Can it be optimal? And let's consider moving now along the surface, because I'm only allowed to move along the surface, because if I'm not on the surface, I can always do better. So if I move this way, look, I go to a higher contour and I increase the in-sample error. But if I move this way, I go towards the lower contour and can decrease the in-sample error. Okay? And so the point that I'm going to rest at, which is the minimum, can never be such that the contour intersects in this way. Okay? So I will continue to move. I will continue to move in this direction, continue to move until I get to this point, okay, where the contour that touches me no longer intersects in this non-trivial way, has only one point of intersection with me. And how do we see that this is now the optimal? We see that this is the optimal because if I move this way, I'm moving to a higher contour. And also if I move that way, I'm moving to a higher contour. So the optimal has to be a point on my surface which is tangent to a contour of constant in-sample error. So the optimal has to be a point on my surface, my constraint surface that is tangent to a contour of constant in-sample error. Okay, so the contours of constant in-sample error in red, and I'm at a point on the surface of my constraint which is tangent to that. Okay, now let's look at what's happening here. Now remember, I just told you that at this point, so on the contour, if I take the gradient, it's always, it's pointing, in the normal direction away. So this is the direction of E in, gradient of E in. Okay, and let's look at the normal to my surface, because this is a sphere. Now this can be generally, in a more general setting, I can look at the gradient of my surface. Okay, my surface, which is this surface is defined by the function W transpose W minus C equals 0. So on this surface, we have a function that is constant. If I take the gradient of this function, I get the normal to the surface. Okay. But in this particular case, we all know what the normal to the sphere is. That's one of the convenient reasons why I chose the sum of the weights. The normal to this surface is exactly, in the direction of the weights. So if these are the weights W, in that direction W is the normal to the surface. And what do we observe? That if you're at an optimal, the gradient of the in-sample error is in the negative direction of the gradient to the surface defining the constraint. In this case, is in the negative direction of W. Okay. So what does that mean? That a necessary condition for being at an optimal is that the gradient of the in-sample error is proportional to minus W. In a more general setting, this would be replaced by minus the gradient of the function that defines the constraint surface. Okay. Proportional to means it's equal to some constant times that. So let me introduce a constant lambda sub c. Okay. Sub c because it depends on c. Okay. And I will write this as the gradient of the in-sample error is equal to minus lambda sub c times W. Where lambda sub c is, now if you're familiar with Lagrange multipliers, lambda sub c is called the Lagrange multiplier, and it has to be positive because they're in opposite directions. So lambda sub c greater than 0 is known as the Lagrange multiplier. Now, I won't discuss the general theory of Lagrange multipliers and what to do if you have more than one constraint and so on and so forth. But in this example, the geometric intuition suffices. Okay. But for mathematical convenience, I can any constant times this will suffice. So I'm going to put a 2 in here just for mathematical convenience. Okay. So if it was true with some lambda sub c, it's certainly true with, taking half of that and multiplying by 2. Okay, so this is a necessary condition, okay, for us to be at the inequality constrained minimum error solution. Okay. So that's a necessary condition for us to be at the minimum error inequality constraint solution. So this is a necessary condition. Must be satisfied. Okay, this is E in of W. Okay, let's see where that mathematically leads us. So where does that lead us? Well, let me take this to the other side. So the gradient of the in-sample error of W plus twice lambda sub c W is equal to 0. And I observe that twice lambda sub c W, this is exactly the gradient of lambda sub c W transpose W. And what this means, so in the more general setting, I would have a gradient here, but now I've replaced the gradient here because this gradient is exactly that. Okay. Think of this as W squared, so it pulls down a 2 and then you get W. Okay, so we have, and since the gradient is a linear operator, the gradient of the in-sample error plus lambda c W transpose W, that must equal 0. And so that's why we put the factor of 2 in here. It just makes it less ugly to have just this one constant here. If we didn't have the factor of 2 here, we'd have a 1/2 here. Okay. And, what do we observe about this equation that we have derived? We're claiming that if you add a solution to your constrained error minimization, then it must be the case that the gradient of this function should be 0. Okay? But if the gradient of this function should be 0, then that means both of these are positive functions. If the gradient is 0, okay, then that means that this function in here is minimized. So E in of W plus lambda C W transpose W is minimized. That's where we wanted to go. Very interesting. Okay, so let's summarize. So we're looking at the second situation where the solution is not trivial. So let's summarize. So we started with an inequality constrained minimization, and we played all of our, magic with the geometric view and so on and so forth. And we have come down to an equivalent condition. So this is minimized if something else is true. And what else is true? This is minimized if this guy is minimized. So this guy, this problem is solved if the following problem is solved. Minimize E in of W plus lambda C W transpose W. Minimize this guy. Okay. Subject to what constraints? No constraints. No constraints. So this is an unconstrained. So unconstrained minimization. Much more convenient. Okay. Unconstrained minimization. So we started with a constrained minimization, minimize the in-sample error subject to this constraint, and we have now reduced it to an unconstrained minimization. Except that, when there's no easy way to decide what lambda C should have been. So you gave me C, let's say C equals 1. Well, that means that there's a corresponding lambda C, the correct Lagrange multiplier that corresponds to C equals 1. So lambda sub C, the only catch is that lambda sub C is a function of C. And let's see if we can understand the sort of high-level dependencies. So what is this lambda sub C doing? When we go and minimize this in an unconstrained way, so we try to minimize this guy, try to minimize this guy. This guy is encouraging the weights to be small. So the larger lambda sub C is, the smaller your ending weights will be. Okay? Which means that you will satisfy a smaller budget. So when lambda C goes up, that corresponds to C going down. So if you decrease your budget here, you will correspondingly have to increase this guy C. If you increase your budget, you will decrease this guy C. If you send your budget to infinity, this guy will go to 0. Okay? But the catch is that, yes, I have to do an unconstrained minimization, but I don't know what lambda C is, because it depends in a very complicated way, typically, on C. Okay. And so it appears that, we have translated, we have sort of exchanged an inequality constrained minimization for an inequality constrained minimization for an unconstrained minimization, but with some unknown parameter lambda C. So we're not going to be able to do this anyway, except things are much, much better than they look. Okay. And why? Okay. Except, remember what C was. C was the budget. C was the budget. Who got to choose C? I got to choose C. I said that I'm going to do my fit in a constrained way using, modulo a budget of 1. Well, if I get to choose C, that's equivalent to me getting to choose lambda sub C. Now, it is true that there's no nice intuitive interpretation of lambda sub C as a budget. I'm giving you a budget of weights. But you can equivalently view it as, I'm placing a penalty on the size of the weights instead. Okay? So rather than giving you a budget on the weights and choosing C, I can choose lambda sub C and view that as a penalty that you're going to pay that depends on the size of the weights. Okay? And instead of doing an inequality constrained minimization, I'm going to do a penalized minimization, but it's going to be unconstrained. And because I get to choose C, well, I might as well, forget about now that world with, my constraint hypothesis set H sub C, and instead just choose lambda sub C. Choose the amount of the penalty. So since C was the budget, I got to choose it. So I might as well equivalently, I can choose lambda sub C and do unconstrained penalized minimization. Okay, so now I've exchanged. So I would still have to choose C, and equivalently, I still have to choose lambda sub C. I don't need to know the mapping from C to lambda sub C because I can just forget about that world now. That world was brought in to justify the fact that if you have a constrained hypothesis set, okay, then if you fit with this constrained hypothesis set, you're going to get better generalization, and so things are going to be better out of sample if you can fit well in sample. What we have done is we have said, well, that's equivalent to, instead of picking a constraint instead of picking a budget constraint, just pick a parameter lambda sub C and do a penalized optimization. And in the back of your mind, you have the sort of comfort of knowing that lambda sub C corresponds to some C. We just don't know which one it is. And we do know that lambda sub C going up corresponds to a smaller C, and lambda sub C going down corresponds to a bigger C. So in that sense, we have sort of a principled way, a reasonable way of picking this guy. If we want to add more constraint, we send lambda sub C large. If we want to add less constraint, lambda sub C small. Okay? Okay. So, conclusion. Conclusion. Fitting under a constraint, i.e. budget, corresponds to, i.e. budget C, corresponds to penalized fitting with a degree of penalty with the penalty parameter and this is unconstrained. And now let's just call it lambda. Okay, so we don't need to even emphasize that there's in the background a budget C to which this lambda sub C corresponds. We can just call it lambda. So minimize the augmented error. So we call this the augmented error. Unconstrained minimize the augmented error, E aug of W, which is E in of W, plus lambda W transpose W. Okay. Now, this is the mathematical prescription that is equivalent to fitting the data under a constraint. Okay. Now, just for practical consideration purposes, okay, it's useful to divide this lambda by n. Okay. And that's because, typically when n is larger, you can afford to have less of a constraint. So what this and typically the behavior is linear. Now, I can always do this because lambda is a parameter I get to pick. So let me just pick lambda over n instead. But what this does is it makes lambda more stable across different data set sizes and so on. And the idea here is that, if you want to penalize less when you have more data, give yourself more freedom, then, you should choose lambda smaller when you have more data, and this accomplishes that. So this is just a mathematics. It's without loss of generality, but it makes practical sense. Okay. This is called the augmented error, and you will notice what we have accomplished. The augmented error, which we're going to minimize instead, which corresponds to minimizing under a constraint. The augmented error is exactly equal to the in-sample error plus a penalty term which depends on W. Okay. plus a penalty term which depends on W times lambda over n. You can think of this penalty term that depends on W as penalizing the complexity of the hypothesis, because now remember, go back to those Legendre polynomials. You know, the larger the weights you have, especially on higher order polynomials, the more complex the hypothesis. And so here, if we define the complexity of the hypothesis by the sum of the weights squared, so by how much of each of your individual modes of Legendres you have, if you define that as the complexity of the hypothesis, then here we're penalizing the complexity of the hypothesis. Okay. And in a more general setting, not linear models, we could define the augmented error of a hypothesis H as the in-sample error for the hypothesis H plus some lambda over n, okay, times omega of H, where omega of H penalizes the complexity of the hypothesis. Okay, so in this setting, our complexity penalty for a hypothesis was W transpose W. Okay, just some notation. This guy here, and W transpose W is called the regularizer. Okay. And this guy here, lambda, is called the regularization parameter. Okay. The regularizer, we get to pick. The regularization parameter, we get to pick. Now, weight decay is one of the most popular regularizers. Okay. And there are other types of regularizers, Tikhonov regularizers, this regularizer, that regularizer, and so on. So there are some standard regularizers. And so the recommendation in practice is, pick whatever standard regularizer you want to pick in order to perform this, penalized minimization, this constraint optimization. So minimizing the in-sample error under a constraint. Okay. The regularization parameter, however, is a real parameter that you have to pick. So we don't exercise too much freedom in picking the regularizer, but we really have to pick, we have to decide how much constraint we want to put on the fitting, and that means we have to decide how much to turn this regularization parameter knob. So you can view this lambda as a knob to turn that dials up or down the complexity of the final hypothesis that you produce. Okay. And now we can compare this with the VC theory, which said that E out of H was less equal to E in of H plus omega of big H. And we have succeeded in our sort of high-level plan of replacing the sort of penalty for the hypothesis set with a penalty for the hypothesis. Okay, fantastic. All right, so we did all this intense derivation and we reduced regularization to a mathematical formulation of penalized in-sample error minimization. Let's see if we can actually get an algorithm, a concrete algorithm for linear models. And it turns out we can get a concrete algorithm for linear models. I'll do that derivation quickly. Okay. And, then hopefully we have saved some energy to see regularization in action, in practice. Okay. So, linear models and weight decay. So we're going to derive now a concrete, algorithm, and within the context of linear regression, so you can easily implement regularization. And then if you use regression for classification, you can use the regularized regression for classification, and it should give you a more robust regression for classification, a better starting point for the pocket algorithm, for example. Okay, now. So the prescription is to minimize the in-sample error plus lambda over n times the product of the weights. Okay, and we get to pick lambda now. We've forgotten about the background world in which we have a constraint, a budget constraint, and we're optimizing. We're just doing penalized optimization where we get to pick lambda. So pick lambda, and we'll discuss that a little bit. And minimize E in of W. So E in of W plus lambda over n, W transpose W, which means that we have to minimize, 1 over n, Z W minus Y transpose ZW minus Y plus lambda over N W transpose W. And now I'll do this quickly because we've seen derivations like this many times. So this means that we need to minimize. Okay, the 1 over N can be ignored, so minimize ZW minus Z. So W transpose W, W transpose Z transpose Z W minus twice W transpose Z transpose Y plus Y transpose Y plus lambda W transpose W. So this is equal to, minimize W transpose Z plus lambda I W. So here's W transpose Z W, and then here's W transpose times lambda I times W gives me this term, minus 2W transpose Z transpose Y plus Y transpose Y. And we take the gradient of this and set it to 0, we get the regularized normal equations. So we want that twice Z transpose Z plus lambda I minus twice Z transpose Y equals 0. And when we solve this, okay, assuming now, typically, this is positive semi-definite, but this is positive definite. So now this is always invertible. So that's another advantage of regularized, of the regularization of the regularized linear model. Weight decay, by the way, is just referring to that regularizer, the norm of the weight squared. So this guy is always now invertible. Okay. So that regularizer, this W transpose W, makes this in-sample error minimization. It always makes it stable. Okay, so solving for sorry, I left out the W here. So this is W squared. When you take the gradient, you have W. Solving for W, you get that W is equal to Z transpose Z plus lambda I inverse Z transpose Y. Okay. And so this we call W regularized. Remember, W lin was very similar, except that you can recover W lin by setting lambda to 0 if this is invertible. So W lin was Z transpose Z inverse Z transpose Y, which corresponds to lambda 0. Okay. So this is regularized linear regression with the feature transform. Okay, so let's pass all those words. Regularized, so you have regularization, you have this penalty term, and you get to pick how much of the penalty term to have. And the more you pick, the smaller the resulting weights, because you're penalizing complex weights, you're penalizing large norm weights. So this corresponds to complexity being defined as the norm of the weights. Okay, so this is where the regularization is. You get to pick how much regularization, the knob, to turn up or down. Okay. Feature transform, because we're in the Z space. Okay. And so we can do regularized regression in the Z space. Fantastic. Okay, so let's erase. And now let's move to some experiments, and I'm going to show you regularization in action. And we'll use the slides. Okay, so hopefully we've saved a little energy to see some results from applying regularization, at least in the context of linear models. So remember this example that started the whole discussion. So, we've got the second order target function, the quadratic target function, 5 data points with a little bit of noise. Okay, and you do the unconstrained, unregularized fit. You just fit the 4th order polynomial and you get nonsense. Okay, so now let's talk about regularization. And we're going to add a very tiny amount of regularization. So what happens when we do regularization? Instead of minimizing just the in-sample error, we minimize the in-sample error plus the penalty for the hypothesis complexity. And we're going to choose lambda to be very, 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 very tiny. I mean, almost minuscule, almost not there, but just enough. There's a little bit there to sort of constrain the learning, to put on the brakes. Okay. Now, the other important thing I want to mention is, I'm going to stick with the 4th order polynomials. I'm not changing the 4th order polynomials. I'm just adding the penalty to the in-sample error, getting the penalized error, and minimizing this penalized, in-sample error. Okay, this regularized in-sample error. So let's see what happens when we just add a tiny bit of regularization. Okay, a tiny bit of lambda. Bam! Wow! Okay. Now, if that is not enough to convince you that this regularization works magic, okay, then I don't know what can. Okay. So there was a little bit of noise. A little bit of noise led the learning astray. We have state. So that red curve that we have fit now is actually a fourth order polynomial, but with a tiny bit of regularization. Now let's see what happens when we add more regularization. Maybe things will get perfect. Okay, no. Okay. And so this is what I meant when I said that you really do have to choose lambda. Now we only need a little bit of regularization, it turns out, because remember, what's overfitting? Overfitting is when the noise leads you astray, and the regularization comes to put on the brakes when you start fitting the noise. And in this example, there's very little noise. Okay, and so you need a little bit of regularization. If you put too much regularization, that was the side effect that we talked about. Now, we've gone from overfitting to not fitting the target function. So overfitting is I'm fitting the noise. Okay, and once I put too much regularization, I'm constraining the learning too much, and I'm not fitting the target function anymore. Okay, I'm just trying to get the lowest complexity hypothesis. Okay, and so we call that underfitting. So overfitting, I'm being led astray by fitting noise. Underfitting, I'm not fitting the target function, and there's a sweet spot in between. Okay, and this lambda equals 0.0001, this small amount of regularization turns out to be best. So you cannot just take an unlimited quantity of this medicine that we are calling regularization and expect it to work. It's possible to underfit with taking too much of this regularization, too much of this medicine. Okay, and here's a curve. So this is real data that illustrates sort of what's going on. Okay, if lambda equals 0, you have heavy overfitting. And as you increase lambda, you're going for a higher and higher in-sample error because you're putting more and more constraint. But it's still good. Your out-of-sample error is dropping. So you're in the overfitting regime, okay, where by going for higher in-sample error, we're getting better out-of-sample error. So that's the overfitting regime. And at some point, now you've got just the right amount of lambda, just the right amount of regularization, and then at some point it starts getting worse. Here now you're starting to fail to fit the target function, and so you're underfitting. Okay? So, there is this sweet spot lambda. Okay? Now it's reasonably flat, and what you will observe is that in general it's okay to choose lambda a little bit bigger than warranted, okay, because the price you pay for overfitting is huge. The noise can really slam the learning and kill it. But the price you pay for underfitting is usually small. It's just that you're, not being able to capture all the nuances of the target function. So with that in mind, it's usually beneficial to err slightly on the side of more penalty than less penalty. Okay. Now, I showed you here that, we need only a little bit of regularization because there's only a little bit of noise. And indeed, if you add more noise, now you need to add more regularization. And okay, there'll be a small price you pay for underfitting, for not being able to fit the target function, but it's the noise that's killing you when there's a lot of noise. Okay, and this is illustrated in this picture here. So, here's the out-of-sample error, and the various curves are different noise levels, 0, 0.25, 0.5. So, we're roughly speaking increasing the noise level. Okay, when there's no noise, you don't need regularization. Okay, and that was the original argument, that if I had, even in that simple problem, if all my data was on the blue quadratic, I don't need regularization. The straight fourth order fit will get me a perfect fit to the target function. Okay, but now as you increase noise, your in-sample error looks like this. It's similar to the curve we just saw, and as you can see, if you have no regularization, you're dead. You get a huge in-sample out-of-sample error. But as you add regularization, then there comes an optimal lambda, and then you start underfitting. Okay, and if there's more noise, the optimal lambda comes later. So what does that mean? That means that with more noise, in order to get the best performance out of sample, you need more regularization, which makes sense. But there's more noise leading you astray, you need to brake more. Lambda is your brake. Okay, so now we've developed a brake that we can use for complex hypothesis sets to prevent them from overfitting to noise. But look, this thing I told you about deterministic noise is not a fiction. It's not something we made up. Okay, here are the same curves, but now instead of looking at varying noise levels, let me look at varying target complexity levels, and you see exactly the same picture. So here we're fitting with the 15th order fit, and when the target complexity is 15th order, you should use no regularization when there's no noise. So there's no stochastic or deterministic noise. But when you double the complexity of the target function, now you've added deterministic noise. There's an optimal lambda. Slightly bigger than 0.5. You make the target function more complex, you've added more deterministic noise. You better increase lambda. So there you go. You have to focus on simpler models as the target complexity goes up. Golden. That's golden. Okay. Like I said, there are two things that we have to choose. We have to choose the regularization lambda, or how much to turn up the brakes, how to set this knob that controls the fitting, that controls the overfitting, which is the parameter lambda. And you also have to choose the regularizer. So we discussed weight decay, W transpose W, but there are variations of weight decay, and there are all kinds of regularizers. Okay, so here, look, this is weight decay. This is what we discussed. Okay, the norm of the weight squared. But you could think about, the sum of the weighted square, the sum of the weight squared, but each time weighted by some value, indicating how important is that, power in your is the qth order, the little qth order, power in your final hypothesis. So this is, when Q is large, this is a bigger penalty. When Q is small, this is a smaller penalty. So you can think of this as encouraging lower order fits. So further decreasing the penalty, further decreasing the complexity. So the curve, the comparable curve, is this red curve, and again, there's a huge price for no regularization, and then you drop very significantly, getting close to 0.6. But now the penalty for underfitting for too large a lambda is a little bit steeper. Okay, so you see that this behavior is different. You can get comparable to 0.76. Okay, and let's look at indeed a very weird type of regularizer, which is, instead of the sum of the weights squared, what about the sum of 1 over the weights squared? So now you're encouraging the weights to be large. This is weight growth. Well, that's a perfectly fine regularizer. You give a budget for the sum of 1 of the weights squared. Okay, and weight decay is this blue curve, okay, that we saw before, and this regularizer that we're proposing here, which is weight growth, is this red curve. And sure enough, the optimal regularization parameter is 0 with weight growth. So it's saying don't encourage the weights to be large. And there's a non-zero regularization parameter recommended when you're doing weight decay. So it seems like so there are good regularizers and bad. Weight growth is bad. Weight decay is good because it results in a positive regularization parameter. But even among the good regularizers, there are differences. But you're okay if you can choose the right lambda. Okay? So, one of the things that we need to discuss is how to choose lambda, because if we can choose lambda well, then even if we have the wrong regularizer, we are still okay. Here we're around 0.76 in out-of-sample error. Here we're around 0.76 in out-of-sample error. Comparable. Okay. Now, how to choose the regularizer? Okay. So, let's go back to philosophizing. Okay. So, what does the regularizer do? The regularizer is constraining the model. So what's going to be the perfect regularizer? The perfect regularizer is to constrain the model. So remember, we're going for simpler and simpler hypothesis sets. And remember, what's the perfect hypothesis set? It's the single hypothesis that's F. Well, we're never going to be so lucky, but we can try to constrain the hypothesis set in the direction of F. But now we're going around in circles because F is not known. Okay? So let's instead step back and look at what's the general principle here. The general principle here is that the regularizer and the regularization parameter, but the regularizer in general, is trying to penalize or is trying to constrain your ability to fit noise. Okay. And noise is in some sense the most complex thing that we can think of, especially, and explicitly so when the target function is hypercomplex. Okay. So when the target function is so complex, then you want to prevent your ability to fit complex things. Okay. For example, noise. And preventing yourself from fitting complex things means that your regularizer should encourage hypotheses that are less complex, and this typically means smoother because noise is very jagged. Okay? So the best kinds of regularizers to pick in practice are regularizers that penalize complexity, wiggly behavior of the hypothesis. Okay? And hence weight decay as opposed to weight growth. So weight decay encourages you to fit with a smoother, simpler hypothesis. Weight growth encourages you to fit with more complex hypotheses, and weight decay being constraining you to simpler hypotheses affects your ability to fit the noise and not your ability to fit the signal or the signal that you can fit, because by definition the signal that you can fit is simple. It's the noise that's complex, and so the cure outweighs the side effect. Now, if you choose the wrong regularizer, we can still survive if we can pick the right regularization parameter. And that's one of the applications of validation, which we will discuss next. Okay. So, summary. How does regularization work? Okay. You've got noise in the data. You always have noise. You always have noise. And now you can select good features to try to reduce deterministic noise. you cannot do anything about stochastic noise. So you always have noise in the data. Okay? Take that as a fact of life. And noise in the data will lead the learning astray. Okay? That's another fact of overfitting. So you have to do something about it. And so that means you have to regularize. You have to constrain the ability of the hypothesis set to go after fitting the noise. And why do we have to do that? We have to do that because in order to learn in any useful way, we have to use hypothesis sets that have some reasonable level of expressive power. And once you have a reasonable level of expressive power and there's noise in the data, that expressive power can be led astray. And so we have to constrain it. The alternative is to learn with the simplest possible hypothesis set always, okay? In which case, it's hard to lead such a hypothesis set astray, okay? But then you won't be able to model complex target functions, period. Okay? You won't be able to succeed in learning, very often. Okay? So we need to learn with reasonably sophisticated hypothesis sets, but there is always noise, so we have to regularize. We have to be able to rein in the ability of the hypothesis set and the learning algorithm to fit the noise. Okay, now we can view this in two ways. One way is, the VC angle, where regularization corresponds to a constraint, which corresponds to a simpler hypothesis set, which means that if you can fit with a simpler hypothesis set without, sacrificing too much, then your out-of-sample error will be better, a la VC angle, a la VC analysis. Okay. Alternatively, we can view from the bias variance approximation generalization trade-off. Regularization, sacrifices a little bit of bias for a huge improvement in the variance. But if that huge improvement in the variance comes at the expense of a huge bias, huge underfitting, then it may not be useful. Okay, so these are the trade-offs that exist in sort of regularization. But one thing that is for sure, it is absolutely necessary because there's always noise in the data, stochastic and deterministic noise. Okay. And let's conclude, with the augmented error, which is what we derive today. Okay, so the augmented error is the penalized in-sample error. So it's the augmented error for a hypothesis H, is the in-sample error for the hypothesis H, penalized by a complexity term omega for the hypothesis H. So you penalize the complexity of the hypothesis, okay, and then you have a knob to control how much you penalize this guy lambda. In our case, omega of H was weight decay, W transpose W. The VC angle is that E out of H is less than or equal to E in of H plus a penalty for the hypothesis set. Okay? And so we've managed to replace the penalty for the hypothesis set with the penalty for the hypothesis. And what we found is that, the augmented error, when we minimize that, can be better than minimizing just the in-sample error. Because of this ability for the hypothesis set to just get totally, misled by the noise and overfit the noise and have very bad out-of-sample error. And that out-of-sample error, so the VC analysis is general, and what that means is this error bar is huge. It has to take into account the possibility of being led astray by noise. Okay, so this error bar will be huge. Okay, but the minimizing the augmented error is typically resulting in much better performance because it prevents you from overfitting the noise. And that suggests that there are many situations, especially when there's noise, where the augmented error is beating the in-sample error as a proxy for the out-of-sample error. Okay. So the augmented error, minimizing the augmented error is better than minimizing the in-sample error because the augmented error, which has this penalty for the complexity of the hypothesis, is more accurately mimicking the out-of-sample error. Okay. The regularizer rules of thumb, we choose regularizers that encourage smoother fits, less complex fits, because the thing we're trying to avoid fitting is noise, which is hyper complex. And that leaves us with the sort of task of setting the amount of regularization, the lambda. Okay. And we will discuss validation next. And validation is a tool for choosing this guideline.